Hi, class. So what we're going to look at now is some of the reactions of alkanes. All right, and halogenation and combustion are the two biggest reactions that alkanes do. All right, so we'll talk about combustion at the end, but let's start with halogenation. So halogenation is literally putting a halogen on an alkane. All right, so the way this works is that you're going to take some carbon group, right, and you're going to react it with a halogen. Right? Typically, it's chlorine and bromine, but we'll talk about the other ones as well. And we've got to have something to kickstart the reaction. Right? So one of this first sentence says, if you kept methane or any alkane and chlorine in a dark room, nothing happens. The mixtures just kind of go their separate ways. However, if you expose the groups to heat or light, then what you start to see is the reaction. Right? And once the reaction begins, it's actually going to give off heat, right? So it's very exothermic. All right, so it needs heat to get started, to get over that initial energy barrier. But once it goes, it actually is exothermic and gives up a lot of heat. All right, so what we're going to actually see is the halogen is going to replace one of these hydrogens. So we had 4 hydrogens to begin with, and now we have 3. We only use one of the halogens, and so that's why our byproduct is HCl. So it's the chlorine we didn't use and one of the hydrogens. All right, what this is going to lead into is one of the reactions that we're going to talk about. So substitution is in a reaction where we substitute one group for another group of atoms. Right? And it can be a single atom or it can be a group of atoms. And so in this case, what we're going to remove is we're going to substitute a hydrogen and a chlorine. Right? So we're going to substitute a chlorine for one of the hydrogens in that methane. And so that's why we see it as CH3Cl2. And we can do this substitution over and over, right? So in this class, we'll mainly look at the mono substituted, mono mean one, but you can keep doing this over and over. And so one of the best examples of this is Teflon. So Teflon is where you've swapped out all of the hydrogens for fluorines, right? So we've substituted a fluorine for every single hydrogen. Okay? So if you did this stepwise, there's CH3, we do the reaction, 1 chlorine takes the place of 1 hydrogen. So that's why it becomes CH2. And every time we do this, we produce HCl. We can do it again. So we pull off another hydrogen, replace with a chlorine. So we get CHCl3, and then we get all the way to we get to carbon tetrachloride. Same thing would happen if it's bromine. We rip off a hydrogen, put a bromine in its spot. Okay? And so we can just keep going very sequentially. Now, this one adds a little bit wrinkle to it. On methane, it was nice because it didn't matter, right? All 4 hydrogens were exactly the same, so which one we changed didn't matter. There is some regioselectivity. So regioselectivity just means we're going to pick what region of the molecule we're going to enter. So if you're looking at this first molecule, these hydrogens on the end are exactly the same, right? Because you could flip that molecule over and they'd be the exact same spot. But the ones in the middle are different. Okay? So our choice now is, do we want to put the bromine in place of one of the orange hydrogens, which is on the outside, or do we want to put it on the inside? Right? The 2 on the inside are exactly the same. The 6 on the outside are exactly the same. Right? And what you'll actually see is that bromine in particular has a really high preference for the more substituted carbon. Okay? And remember, the more substituted carbon is the inside one, right? The one that's attached to more carbons. So if we're looking at this one is a secondary carbon because it's attached to 2 groups, 1, 2. The ones on the outside are primaries because they're only directly bound to 1. And even though there's 2 carbons along the chain, it's only sharing a bond with 1 carbon. So these are my primaries. So the more substituted you are, the higher the preference for bromine. So if you give bromine a choice, it will always pick the more substituted carbon. Chlorine has that same preference, right? So it would still like to be on the more substituted carbon. So if we pick these versus these, it's always going to pick the more substituted. The problem is that preference is so much smaller, right? That even though it wants to pick the more substituted, statistically, there's a lot more hydrogens on the outside. So now the problem with chlorine is that difference or that preference, right? is not as great so that it's not going to dictate the entire reaction. So for bromine, it's just based on you're going to put the bromine on the more substitute. And we get a tiny bit of the other one, but we kind of ignore it. The problem with chlorine is you have to weigh two things. It does have a slight preference for the more substituted, but it also does the number of hydrogens, right? So the total number of hydrogens are the more chances it can go there. And so if you notice here, the differences really aren't that great. Right? And so while there is a slight preference to it, it doesn't show up as great because it also weighs the total amount of hydrogens in each one of those spots. And I'll show you that here in a second. All right, so if we have our regioselectivity, these are our numbers. For bromination, if you have a tertiary carbon, that compared to a primary is 1600 to 1. So for every 1600 molecules that the bromine gets added to a tertiary, you'll add 1 to a primary. Right? So that's why we kind of ignore it, that we just say the more substitute, the better. Secondary to primary, right? 80 to 1, so that's still really good. And then even secondary to tertiary, it's 1600 to 80. Right? So that's a huge difference. Chlorination has that same preference, right? We're going in this order here, tertiary, secondary, primary. 5 to 4, so between a secondary and a tertiary, yeah, it likes the tertiary more, but it's not as great, right? And the same with the primary. And so the problem with chlorination is we tend to think of it as having more of a random mixture, because if you have 6 primary hydrogens to 1 tertiary, you've already canceled out this preference because there's 6 more of those primary hydrogens. So it's always a balance between the number of hydrogens and the preference. All right, so let's try this one here at the bottom. So if we take our molecule here, so 2-methylpropane, it's got these primary hydrogens on the outside, and it's got a tertiary hydrogen in the inside. In this case, we're using bromine. So anytime we see bromine, we're going to say it's going to add to the more substituted carbon. So we're going to rip off that green hydrogen and replace it with a bromine. We need heat or light. And so here'd be our formula. And then if we drew the molecule out, you can see this carbon was the one in the middle. Here are 3 CH3 groups. And so instead of having that green hydrogen, we ripped it off and replaced the bromine. All right, so that would be our major product. We'd get a tiny, tiny amount, 1 or 2% of substituting that hydrogen on the outside for a bromine. But when I ask you, we're typically going to do just the major product. So this is the only thing you want. All right, let's try one. So Br2, and let's use light. So H nu is for light. So go ahead, pause the video and draw me the major product of this. All right, let's see how everyone did. So you're going to keep the carbon chain exactly the same. If it's bromine, we're going to find the more substituted carbon. So it's this one in the middle. And then we're going to put a bromine off of it. And then our side product is always HBr. Right? So it's the hydrogen we ripped off, we'll put the bromine in its place. All right, let's try one more with chlorine. We can take Cl2. Remember, it doesn't matter if we use heat or light, we just need something to kickstart the reaction. All right, so again, pause the video, draw me the major product of this, and then we can do it together. All right, so if we're looking at this, we're always going to keep the carbon chain just the way it was. Those should be connected. Now, in this case, all 6 of these carbons are equivalent, meaning they're exactly the same. And there's 2 hydrogens implied on each one of these carbons. So we're just going to pluck off one of those hydrogens, replace it with a chlorine. And then don't forget, we always get as our byproduct HCl. It doesn't matter which one of the 6 because they're all equivalent. And so we can use HCl. So that's when chlorine's most useful, is when there's kind of this preference that it doesn't matter, right? Like that there's not a preference between any one of the carbons, right? That they're all the same. So whether you added the chlorine to the one on the bottom, the left, the top, doesn't matter, they're all the same. So that's when chlorine is really useful. Bromine is really nice because it adds to the more substituted carbon. All right, so now that we know what the product's going to look like, let's pause and actually look at the reaction, right? So how does this actually happen, and why do we need lighter heat? So when you see these little fish hook arrows, if it has these barbed or fish hook arrows, it means 1 electron. So if you think back to the beginning of the class, a line means 2 electrons, and so we're literally going to split it. 1 electron on the chlorine, 1 electron on the other chlorine. And that's what these red dots are representing, is those extra electrons that we split apart. Okay? So this is the initiation. That's why we've got to kickstart the reaction. Now, this is how you produce that side product, that HCl or HBr. We said it's a substitution reaction, so we got to rip off one of these hydrogens. So the chlorine is going to come in here and get this hydrogen to give up one of its electrons. And so now these two are coming together, so they're going to make that bond. This other one is going to put that radical, right? So when it's a 1 electron, it's called a radical. So this is why it's radical chain mechanism. We're going to put that radical on that carbon. And so there's our radical electron. We have the same thing up here. Now, once that radical is formed, this is why it's a chain reaction, is we need a little lighter heat to kickstart the reaction, but now we've created some of these, right? So now we can go up and grab another chlorine. So here's a chlorine molecule. And the same way that the chlorine enticed one of those hydrogens, we're going to come here and make a pair. So that's why we make that carbon-chlorine bond. And now we have another chlorine. They can go start another reaction, right? We keep generating more radicals. And so even when we're making products, we're creating more radicals to go forward. And so this just keeps happening over and over and over and over. At the end, we're going to try to terminate the reaction. And so we're going to just try to quench some of these radicals. And so you do get a little bit of these side products in this class. We mainly talk about like the major product. In lab, sometimes we'll talk about doing an extraction or a filtration or some other purification product. So one of the tough things is, while we don't tend to draw these as our side reactions, most reactions have some amount of impurities because they produce some other side products or leftover starting material. And so the hardest thing, especially when people are making molecules, is typically to purify them, because you want to get rid of the junk, right? All the stuff you didn't want. But I digress. So what we're actually talking about here is the termination. So just these radicals coming together to make single bonds to stop the reaction. One last thing. So when we do stereochemistry, if you have a stereocenter, if you lose it, then you don't have any control of it. So when you make these products, if we make a new chiral center using these radical reactions, we're always going to get a mixture of both. Right? So one thing you can do is pause the video and show me what the product of this reaction would be. And then we'll go through it together. All right, let's see how everyone did. So we can pick CH3, CH, and then we're going to have a bromine up on top, CH2, CH3. And then let me just highlight again like we've been doing. You could have picked either one of these two hydrogen groups. They're exactly the same. I picked the one on the left, but it doesn't matter. And then the ones that are different are the two outside ones. So they're different than the green, but those two are equivalent. Now, what this is talking about is we could have either have made this chiral center here wedged or dashed. Right? And so the problem is, remember when we draw this? So let me draw it out, CH3, carbon. Now, we have this molecule, right? And we can draw this product, or we could have gotten the exact opposite. So the stereoisomer where the bromine is wedged. So I'm going to squeeze it in there. And so we actually make both stereoisomers. And the problem is this reaction just doesn't give us any control of that group. So the only thing you have to be careful about this is if you make a new chiral center, you're going to get both the wedge and dash. So the bromine would be both wedge and dash, meaning you get both the R and S. And what we talk about is it gives you a racemic mixture, right? Meaning you have both stereoisomers. So again, we've used our hand analogies. We would make both hands, the right and left. Right? So that's the only thing you have to be careful about with these reactions. Last two things. So this is a compound that actually people use a lot, is NBS, right? So N-bromosuccinate. And it's just this fancy bromine molecule here. And what it does is it actually adds a bromine to the allylic position. So allylic means one away from a double bond. All right, so what I would talk about or put a note about is this means one away from a double bond. All right. So when you brominate something allylically, it means you did it one away from the double bond. So this is actually going to have our double bond here, and we're going to put the bromine one away from it. All right. So we're going to deliver this bromine, put it right here. All right, so pause the video, give it a try, and we'll do it together. All right, so we keep our molecule, right? So we're gonna have our cyclohexene. In this case, we're gonna keep the double bond, and we're just gonna add that bromine to that allylic position. Right? You could have put it here on the bottom as well, so that'd have been fine. It's just one away from the double bond. Right? And then this just gets the hydrogen. Right? So in our product, draw very well. It just becomes our H. Other two things, this is my light, right? So this is the light. This here is just my solvent. So one of the things you'll see when we go to lab is you gotta put a lot of times if these are both solids or one's a solid, one's a liquid, and they don't mix, you need a solvent to help them mix so that they can bump into each other. So the chemical reactions take place when there's collisions. So we need these collisions for the reaction to take place. We gotta bump them into each other. All right, so this is just my solvent. So it's not involved in the reaction. And this is just the shorthand for light. Okay. So when you see NBS, you should think that it's going to add a bromine allylically. Right? So we see NBS, it's going to put a bromine one away from a double. Last reaction. So, well, this is the one we probably use every day, right? So if you drove to campus, you drove anywhere, you heated your house, you're doing some amount of combustion, right? So combustion just means we're going to take some alkane, right, react it with oxygen, and then we're always going to produce carbon dioxide, water, and energy. Right? So it's going to kick out carbon dioxide, water, and energy. So here's our generic formula because it really doesn't matter. We can do any alkane, and if you drive, you probably also realize you can also do ethanol, right? So it does the same thing. We're just going to burn alkanes, right, reacting with oxygen, and we're going to produce CO2, water, and energy. Right? And this is what we do is we burn the gasoline to get energy for our car, and so it goes. Same thing's true actually with the food we eat. So if you go in to take biochemistry, our body actually does a form of combustion every time we eat food. And so that's why we breathe out CO2 and we use energy, right? So it's actually kind of neat. The body does it very elegantly and slowly kind of oxidizes the molecules. Same thing here. We're taking our alkane, which is just a carbon chain, and we're going to oxidize it to CO2. So anytime you're oxidizing something, you're putting more carbon oxygen bonds. So the most oxidized form of carbon is CO2, right? And so what we're essentially doing here is harnessing the energy from those bonds. I want to leave you on one last note. As we move forward, we're going to start looking for groups, functional groups, and doing reactions on them. Typically, carbon-carbon single bonds are really strong. So even though we're doing this combustion reaction, it's typically really hard to do stuff with alkanes, right? And so of the groups, they tend to be the least reactive unless we put in this kind of situation where we can force it to do combustion. So typically, unless it's this halogenation or combustion, alkanes aren't going to react. All right, so these are the two big reactions for alkanes. And the reason I highlight that is when we start to get to double bonds and some of our other functional groups, you're going to see that they have a much quicker reactivity, meaning that if there's a double bond, they're going to react much faster than our alkane. And so this is just to highlight that they do have some reactions, but they're very limited. All right, I hope this was helpful.